Hi, this is Wendy Lightheart, and today we're going to look at how to factor some special forms. The first form we're going to talk about is the difference of two squares. That is the difference of two perfect squares. If a and b are real numbers, variables, or algebraic expressions, then if we have a squared minus b squared, then that can be factored into the two binomials a plus b times a minus b. So let's try that on x squared minus 25. Notice that x squared is a perfect square, obviously. And one quick way to check if a variable is a perfect square is if it has an even exponent. So even if it was x to the fourth or x to the sixth, those have even exponents, so those would be perfect squares. And then for the numbers, hopefully you can remember your perfect squares that you learned in elementary school. If not, you might want to do a quick reminder so you can recognize them quickly. 25 is a perfect square because it's equal to 5 times 5. So your first step to use this formula is to identify what the a and the b are. So since we would need to square x to get x squared, the a is equal to x. Since we would need to square 5 to get 25, the b is equal to 5. Once we figure out what the a and the b are, we simply replace the a and b, all the a's and b's on the other side of the formula, with those expressions. So that's going to factor into x plus 5 times x minus 5. So notice that all the a's were replaced with x's and all the b's were replaced with 5's. And if you FOIL this out, you'll see that you do indeed get x squared minus 25 back. Here's another example. 1 minus 4y squared. Well, 1 is a perfect square since it's equal to 1 times 1. And 4y squared is a perfect square since 4 is equal to 2 times 2. And y squared is equal to y times y. So we first need to figure out what the a and b are. Well, since we would need to square 1 to get 1, the a is going to be equal to 1. And since we would need to square 2 to get the 4 and square the y to get a y squared, that means the b is equal to 2y. So now we just need to use the a plus b, a minus b part of the formula by replacing all the a's with 1 and all the b's with 2y. So that gives us 1 plus 2y times 1 minus 2y. And again, you can check your answer with FOIL. Okay, how about this example? Well, 3 is definitely not a perfect square. Well, don't forget, you always need to check for a greatest common factor. And 3 and 75 have a common factor of 3, so if we factor out the 3 first, then notice that we do have a difference of squares left over, the x squared minus 25. And so we've already used that example before, so remember that the a is going to be x and the b is going to be 5. And so we have x plus 5 times x minus 5 for the x squared minus 25 part. And don't forget that GCF you pulled out in the beginning, make sure it stays out front for your final answer. Very important note here, and an extreme caution, the sum of two squares does not factor. So we just saw how to factor the difference of two squares. But if you have a sum of two squares, that will not factor. So for example, x squared plus 25 is a sum of squares. So x squared plus 25 is prime. You cannot factor it. You can try every combination you can think of, but you'll never get it to multiply back out to x squared plus 25. So just be very careful to pay attention to those signs in between those two perfect squares. The other special forms that we're going to talk about are called perfect square trinomials. perfect square trinomials are trinomials that when factored have the form a plus b squared or a minus b squared. So when you factor them, it results in a binomial being squared. Well, these have formulas that you could use for factoring perfect square trinomials. However, these forms are more difficult to recognize than the difference of two squares and can always be factored using the methods we've already learned so far. So this will be a good review for the methods that we've already learned for factoring trinomials. This first example is a trinomial. There's no GCF to pull out, and notice that we have a leading coefficient of 1. So that means we're looking for two numbers that multiply to give us the c, which is 25 in this case, and we'll add to give us the b, which is 10. Can you think of what those two numbers might be? If not, that's okay. You can try making a table to find those numbers. The numbers are 5 and 5. So we'd place that inside parentheses with x's in the front. And since these binomials happen to be exactly the same, we need to go one step further and simplify this and write this as x plus 5 being squared. That's just a shortcut for writing x plus 5 times itself. So this happened to be a perfect square trinomial. How about x squared minus 12x plus 36? Check for a GCF. We don't have a GCF, so then notice that it is a trinomial whose leading coefficient is 1. So we would write our two sets of parentheses, place our x's, and then we'd be looking for two numbers that multiply to give us 36, which is the c, and add to the b, which is negative 12. So did you think of those numbers? Those two numbers are negative 6 and negative 6. So we place those in the parentheses with the x's. And notice that once again we have a binomial times itself, so we can always simplify that by writing it as x minus 6, the quantity squared. Okay, here's another trinomial. You can check for a GCF, but there is no GCF for this one either. But the leading coefficient, notice, is not 1. So we'll need to use the grouping method that we learned in 6.3, where first, remember, you have to multiply the a times the c. So 4 times 9 is 36. So we need to find two numbers that multiply to give us 36 and add to give us 12. And those two numbers are positive 6 and positive 6. And remember, what we do with those numbers is different when the leading coefficient is not 1. We use those two numbers to split up that middle term into two terms, giving us a 4-term polynomial. So we're going to rewrite that trinomial as 4x squared plus 6x plus 6x plus 9. And that's again using the plus 6 and the plus 6 to split that 12x up into two terms. So now we have 4 terms which we can factor by grouping. So we group the first two terms together, we group the second two terms together, and we pull out a GCF out of each group. So the first group, you'll probably notice that there's a GCF of 2x, and the second group has a GCF of 3. And when you pull those out, you'll get a common binomial factor left over of 2x plus 3. So that's going to be pulled out as one of the factors. And then notice that what's left over is also 2x plus 3. So we again end up with two identical binomials multiplied together, and we can simplify that by writing it as 2x plus 3 in parentheses squared. Here's another example. So look for a GCF first. Aha, this one does have a GCF, right? So we pull out the GCF, which is 2. And when you factor that 2 out, notice that we have a trinomial left over. And the leading coefficient is not 1, so we're going to have to use grouping again. So we would multiply the a times the c, which will be the 25 times the 4, so that's 100. So we're looking for two numbers that multiply to give us 100 and add to give us negative 20. Can you think of what those numbers are? Those numbers are negative 10 and negative 10. So remember that we use those numbers to split up the middle term into two terms. So we'll have this 2 still out front. So make sure you keep the GCF out front. We're going to group these terms after we split the negative 20x into negative 10x minus 10x. And then pull a GCF out of each group. So the first group has a GCF of 5x. The second has a GCF of negative 2. Remember, we have to take out a negative GCF when that second group begins with a minus sign. So when you pull out those GCFs out of each group, you'll have a remaining binomial of 5x minus 2. So that's your common binomial factor. So that will be one of the factors of that trinomial. And the other, notice, is 5x from the first group and a minus 2 from the second group. Put those together and we have identical binomial factors plus our GCF of 2 in front. So we can simplify that a little bit. We still have our 2 up front, but we're going to rewrite the 5x minus 2 times itself as, in parentheses, 5x minus 2 squared. So that's it for today. So just remember that you don't really have to know those formulas for factoring perfect square trinomials because you have all the skills you need to factor them already. So the less formulas to memorize, the better, I think. If you still like to use the formulas, that's perfectly fine, but you'll have to memorize them. So have fun factoring.